All right, today we're going to talk about turbulence. We're going to stay at a fairly high level. Mostly we'll want to talk about things that concepts that will be important for CFD, computational fluid dynamics. There are entire courses on turbulence, but like I said, we're going to stay high level. We'll have 2 lectures here. So to get started, here's a picture of a jet flow. So there's a circular jet. There's fluid being injected into the same fluid here. And it's just got a dye in this case, so we can visualize some of the structure. And there are a number of observations we can make. Notice that these are 2 different Reynolds numbers. And if we just look at the 2 side by side, we can, it's pretty clear that there are differences in these structures, right? So on the left side, I can see kind of these large structures in the fluid, these larger vortices. On the right side, I don't see such big, I mean, there's still the big structures, but I see a lot of really fine structures. In fact, I can't really see them. If I was to zoom in closer, I would see this type of behavior, but because they're so small, it just looks more foggy, if you will. So these are typical features of turbulence, that as we increase in Reynolds number, there are smaller and smaller scales of turbulence that develop. And actually, this is the big challenge of simulating turbulent flows, as we'll see. We also notice that some of the large scale features aren't as affected. For example, the spreading angle seems to be about the same, regardless of the Reynolds number. But this is kind of the characteristic behavior of turbulence, that as I increase that Reynolds number, then the scales of the turbulence that I need to, that are occurring become smaller and smaller, right? There's still the large scale behavior. There's still going to be large scale mixing, but there are other important things happening at smaller and smaller scales. So there are a number of ways we can try to simulate turbulent flow. And the first is what's called direct numerical simulation. And I'm not going to play this video right now, but there are a number of good videos you can go find online. But direct numerical simulation, the concept is conceptually straightforward, which is we know the governing equations, the Navier-Stokes equations. We can discretize and we can just solve them. And that sounds great, and it is, but the problem is, as described here, that as we get to big Reynolds numbers, the scales that we have to resolve are smaller and smaller. So we need finer and finer meshes, and at some point, it just becomes intractable. So for example, in this video, they do a simulation of an airplane. So here's just a simple airplane here, right? And it's an airplane is at a high Reynolds number. And they show a simulation with a lot of cells, so something like 1 billion or so, but it's only capturing this tiny little volume within the boundary layer next to the wing, right? This tiny, tiny little control volume, right? Nowhere close to the entire airplane. And that's already, I mean, an extremely, extremely expensive simulation. And, you know, it's like getting this little centimeter scale thing on this big airplane. So the cost is generally proportional to about Reynolds number of the cube. So this type of approach quickly becomes intractable. In practice, people only use direct numerical simulations on relatively low Reynolds number flows. I'm not sure about the latest, but it's typically in the maybe in the thousands, 100 or 1,000. So a small Reynolds number by engineering standards, and with simple geometries. So for most things, this is just impractical. Okay, so if we can't do DNS, well, what can we do? One approach is what's called the Reynolds Averaged Navier-Stokes equations, or RANS. And here's a good picture maybe of the concept. Actually, this is a grainy picture, but we'll give you the idea that the real fluid flow here on the left has all sorts of mixing, all sorts of behavior. But if I time average, right, if I was to capture all that behavior over some instant in time, let's say I took the velocity and I just averaged it across all of that, and all of those time periods that I've either simulated or I have collected data on in my experiment. I just average it, then I get this kind of behavior that's smooth. And so the idea is that we're going to take our Navier-Stokes equations and average them. We're gonna try to compute average behavior. Now, as you can expect, we're losing a lot of the detail. So whether that's good enough or not really depends on what we're after. If we're after things like forces, which are already averaging, right? We're taking summations, integrations really over bodies, so in some sense an average. And this may be appropriate, but if we want to look at things that fundamentally are unsteady, like we want to look at the pressure fluctuations in terms of acoustics or structural dynamics, or other things that the aerodynamics are going to affect, this type of unsteady loading behavior, then this is not going to be an effective approach. But like I said, for many engineering applications, we're really interested in these integral quantities, and so a time average may be quite appropriate. So to motivate this, I'm just going to quickly review what we mean by an average or expected value. The average, we'll use this bracket symbol to denote an expected value. Sometimes you'll see it written like this, right? E is expected value. And for a continuous function, the definition is that it's just the integral of x across its probability distribution, right? And so we integrate across the entire thing, minus infinity to infinity. In the discrete world, right, if we had a discrete probability distribution, we would just take each event xi multiplied by the probability of that event. So basic review. So the idea that we're going to use is what's called a Reynolds decomposition. So we're going to take all of these flow quantities that are of interest, the velocity, pressure, density, and so on. And we're going to just decompose it as follows. So for example, let's just take the x component of velocity u. We could say, well, that is equal to its average value, right? Because it's varying, let's say in time or in space, but in general it's varying, right? So, yeah, it varies in time across the simulation, right? And we'll say it's equal to its average value plus some fluctuating component. So I haven't made any approximation so far. This is just, this is always true, right? So if u, for example, looked like this, it had some unsteady signal, we could say, well, that is equal to some average value plus, here's 0, right? Some fluctuation about 0. And let's pretend that I could draw that appropriately. So if I took this signal plus this, I could reconstitute my original value. So again, no approximation yet, just simply an observation that any quantity is going to have an average, and then the fluctuations about that average we'll just call this fluctuation value with a prime symbol. So a few properties about averages that you'll need to know, or to do this, we would need to know is that the average of a sum is equal to the sum of the averages. And you could see that if you were thinking about averaging as an integral, right, that we could separate those two integrals. By definition, the average of the fluctuating components is going to be 0. Because we've already taken the average out, this is just, I mean, this is the definition that if that average wasn't 0, then we didn't actually get the right average, right? So this is always true. Averaging this expected value can commute with differentiation. So we could pull the differentiation out of the average. Again, that would make sense if you think about it as an integral, right? That order of differentiation and integration can commute. If I take the average of this product where one of the values is already an average, again, it's maybe easiest to think of an integral sense. Since that's already an average, it's a constant now. I could pull it out of the integral, and so I could pull that delta u out, and so then I'm left with the average of v. And yeah, well, that's good enough for now. So one thing we're going to try to work out is let's work out what is the average of UVs, because that's going to be an important term that we'll see. So let's try to work that out. And you might try this on your own, pause and try it, but let's just work this out and see what happens. So this is going to be actually the average. So now I'm going to substitute in what U and V are, right? U are really, we're going to use this decomposition. So U is the average of U plus its fluctuation. And I need to multiply that by the average of V plus its fluctuation. And then I average that entire thing. So let's just, product rule, let's just break this out. Notice when I do this, I'm going to get a bunch of products and they're each going to be summed. And so I'm going to use this rule that the average of the sums is just the average of each and then summed. So I can break this up into different sums. So I'm just going to do that in one step here. So I would have the average of UV plus the average of U prime V plus the average of U V prime plus the average of U prime V prime. All right, so we can use some of our other rules. This one, for example, we can see we can pull any of those averages out. So this one can come out, this one can come out, these can come out. So I'd have UV. Notice this one, once I pull that average out, I'm just left with the average of U prime. And by definition, that is 0. So this one is gone. Similarly for this one, also goes to 0. This term, though, none of my rules do anything to, so I have to keep that. So I get this U prime, V prime. And this, as we'll see, is going to be a real challenge here. So if I take the average of a product, it's not just simply the product of the averages. I have to add also this average of these fluctuating components. Okay, so that's going to be important. Offhand, we might initially think that would be 0, right? Because the average of a fluctuation is 0, but it's not the case that the average of the product of two fluctuations is not necessarily 0. Okay, so let's now take what we've learned here and apply this to an example. In this case, this is just a motivating example that applies in general to Navier-Stokes equations, but just for simplicity in writing things out, we'll just reduce it to the two-dimensional case and make it incompressible. But again, the same concept will apply for 3D compressible. Okay, so here's those incompressible Navier-Stokes equations. What we're going to do is we're going to plug in all of those variables, right? So we'll plug in U is U plus U prime, and P is P, average P plus P prime, and so on. So far, doing that, no approximation is introduced. But then after, so once we're done with that, we're going to take all these equations and average the whole thing. So that is an approximation that's being introduced, and effectively we're doing this now, right? We're taking those equations, just trying to smooth out all of that behavior, take the average. So all these rules that we just saw will come into effect. I'm not going to go through this in detail. You can go see the textbook, see my notes on that if you want to see that. I'm just going to jump to the result, and this is it. And what you'll notice if we flip back and forth, like this equation here, if we compare it to this, it's exactly the same, but instead of having the instantaneous quantities, I now have the average quantities, right? And in fact, every term looks exactly the same. Instead of instantaneous quantities, I have average quantities, except, right, all of this is exactly the same. Everything in black is the same, except I get these new terms. Why did I get these new terms? Well, it comes about because of this rule here, right? Because I have these products that I average. The average of the products gives me these additional terms, right? I don't just get the averages out like I would have hoped. I get these additional terms that are an average of products of fluctuations, okay? And this is what causes a problem for the Reynolds average Navier-Stokes equations. I have what's called a closure problem. In other words, I have new terms that I have no equation for. And this is where turbulence models come in. So if you've done any CFD, you've had to select turbulence models, or you've heard about that. Maybe you just use the default, but you probably heard of using turbulence models in CFD, and this is where they come in, right? Because of doing this averaging, I have these additional terms that I have no model for, so I have to create a new model. It's not necessarily purely physics-based anymore, right? Because there's not a pure physics model for it. I'm going to use physics to maybe try to motivate a model, but I don't have a model. I have to invent one. And so there are many turbulence models that exist. These things here, if I was to write it in a general way, UI, UJ, where these are the fluctuating components, we call these Reynolds stresses. And this, written in this form, we call this the Reynolds stress tensor. The reason why we call it that is because it will have a form. This has a kind of a form and similar units to the stress tensor, the regular stress tensor. But it's not a stress tensor, right? It came about because of doing this Reynolds averaging. So we call it a Reynolds stress tensor, or Reynolds stress, or these terms are called Reynolds stresses, because they kind of numerically have a similar role to these regular stress terms, but they came about because of Reynolds averaging, right? They're sort of a mathematical thing that came about. All right, so we have these Reynolds stress tensors. We need a turbulence model. So before we get to a turbulence model, we're going to talk about a few more quantities that will help motivate some of these turbulence models. And the first thing we're talking about is what's called the turbulent kinetic energy equation. And that is formed by taking this equation here, and we're going to subtract it from the original momentum equation here, or sorry, just this one. This is the momentum equation. We'll subtract it from this and multiply by velocity so that we can get things in terms of kinetic energy. And this is the result. Again, I'm not going to derive it, but this looks like it's a rather long equation, but it has some useful concepts in it. So this equation here has this term here, which looks like a total derivative. In fact, it is, right? This is dk dt. It's a total derivative. And K is the kinetic energy. So well, I can write it out like this, right? It's the trace, or it's 1/2 times the trace of that stress tensor. So if I was to write it out specifically in Cartesian coordinates, it would be like U prime. No, let's just write it out like this. 1/2 U prime squared plus V prime squared plus W prime squared. So in other words, it's the kinetic energy associated with these velocity fluctuations. We call this the turbulent kinetic energy. So this is the turbulent kinetic energy. It's K. It's the most fundamental quantity in turbulence. And if you've done anything with turbulence, you would have seen this, but although we often express it in different forms, like for example, in terms of turbulence intensity, which you may have heard of. Turbulence intensity is just another way to express this quantity, but it's in a root mean squared sense and a normalized sense too. So I'm going to take this K, sorry, I'll take K, and I want to get rid of this half, so I'm going to multiply by 2, and I'm going to now divide by 3 because I'm going to take a mean, and I'm going to take a square root. So it's a root mean square of these velocity fluctuations. So I take all these velocity fluctuations, I square them, that's the square. This 2 cancels the half. I divide by 3, so that's the mean, and then I take the square root. So it's a root mean square, right? You could think of it as like an average, right? A root mean square, it's an average sort of velocity fluctuation. And then to normalize, since this is a velocity, right? Because these are velocity squared, and then I square root it, so the units are velocity. I need to normalize by some velocity, and so we would normalize by the mean velocity, right? The average mean velocity. So this is the same concept, right? They're just scaled by some numbers, but same quantity, they're proportional, or at least with the square root proportionality. They're directly related, but that's often how you'll hear it, right? Well, so this is often expressed as a percentage. So we might say this has 5% turbulence intensity or 10% turbulence intensity or whatever. It's a characterization of how much fluctuations there are. So if this is very large, right, these kinetic energy is large, that means these fluctuations are very high, and there's a lot of turbulence, there's a lot of mixing. Whereas if it's very low, then these velocity fluctuations are very small. There's not much turbulence going on. So this is an equation that tells me, this kind of fundamental parameter, how does my kinetic energy change? Okay, so this term here, we see this gradient out front. This is a divergence. So if I call that whole thing on the inside T, we call this the transport term because it's just a divergence. So it's just moving energy around, right? It's a divergence, so it's moving it around. This term here, we often would call it production because it's usually positive. So this is where energy is being created, you could think of. And this term here we call dissipation because it is always negative. So this is dissipation. So kinetic energy is dissipating in this term. So to understand that, we need to write what S is. I didn't really define that. So S is it's the symmetric part of the stress tensor with the fluctuating components. So it looks like this, dui. It's these velocity gradients, but with the fluctuating components. Okay, so I know this is a big thing, but there's some reason for it. For one, to introduce K, which is really important, right? That's the key concept. This is kind of the This is the kinetic energy associated with the fluctuation. So it tells me how much energy is in the turbulence. It's very turbulent or not very turbulent, or we can express in turbulence intensity. But this equation here also tells me something about the physical mechanisms of turbulence. We call this an energy cascade. So how does my energy change? Well, it gets produced. And where is this term going to be large? Well, we see it depends on these velocity gradients with the mean flow. So the mean flow is about these large scale. That's where there's large scale energy. So energy is being drawn from the mean flow at the large scale. So there's these big eddies or whatever, big swirls moving around. And so I pull out energy from there. I transport it down to smaller scales, and this is where the energy is dissipated. This term here is only going to be big at the smallest scales, because remember, these are derivatives of those, these are these velocity gradients. So they'll be large at the very tiny scales, right, where the turbulence is fluctuating very quickly. At the big scales, this term is negligible, but as I zoom into those smaller scales, this term becomes big and it's always negative. So this is where energy is lost. So this basically tells me about how turbulence works. Again, we call this an energy cascade. You could think of it as a mechanism where turbulence pulls energy out of the large scale structures, it transports it down to smaller structures, and then it dissipates that energy at the smallest scales. And those small scales are determined by when this becomes significant. So that'll depend on your Reynolds number, right, where this viscosity and these velocity gradients play a role, right? At the point where that starts becoming significant, that kind of defines those small scales that we have to resolve in our simulations. Okay, so one more thing one more step before we talk about the turbulence models. Common to many of them is this idea, or is this hypothesis, the Boussinesq hypothesis. And this is a simple way to sort of try to build this model. So remember that we've got these Reynolds stress tensors, Ui, Uj, and I don't have a model for it. So I'm going to try to create one. We might say, well, because they have units of stress, maybe we can express it to be like a stress tensor, and we'll use our average quantities. This is what the stress tensor looks like normally, something like this. But we'll use it with average quantities now. And normally, right, it just has new. So let's say, well, let's do the same thing. We'll put a new here, and actually to get the units right, I need to put a minus sign here, because it's actually, if we go back to the equation, right, this has a minus in front of it compared to these. Right, it also appears here as a minus. So I'm taking that stress tensor and I'm making it look exactly like the stress tensor that I have normally. Right, it has this partial UI with respect to xj, except for I use the average quantities, and instead of using the regular viscosity, I'm going to make up this new term, which we'll call the eddy viscosity. So that's going to be another parameter. Of course, now that I have a model, I have a new problem. Actually, I have a couple of problems, but one of the problems is I've created a model, but now I have a new unknown. I don't know what eddy viscosity is. So now I need a model for that. So I'm kind of kicking the can down the road, so to speak. But let's go with that for now. I've used this hypothesis. And actually, this is not complete because this will not work. Because remember, the trace of this term here is my, well, it's 2 times my kinetic energy. If I move the 2 over, the trace of this is 2 times kinetic energy. And the trace of this right-hand side is 0. So this cannot be a good model. So what I could do then is I could say, well, let's add a diagonal component to this. So let's say, let's add, this is the this is my direct delta function. This just is an identity matrix, if you want to think of it as a matrix instead of a tensor. So this is just adding, if that makes it easier to visualize, think of it as identity matrix. So I'm just adding C's along the diagonal here. So this is adding a diagonal component because I need to get this trace to be correct. So if I took the trace of the left-hand side, it's minus 2k. The trace of this one, so this is the trace. Remember, the trace is the sum of the diagonal components of the matrix. This one is 0, and this one is just going to be 3c. So this tells me that c is going to have to be, if I did this right, minus 2/3 k. So I'm going to plug that in, and then I'll get my model. it's going to work, hopefully, which is, and I'm just going to rearrange the order and put the C first, minus 2/3 K times delta J plus nu dui dxj. And don't worry about this. This isn't, isn't making a lot of sense. This is kind of a detailed thing. So this is my model, Boussinesq hypothesis, and it looks a lot like my regular stress tensor. This is the regular stress tensor. This is the pressure term. All right. So this kinetic energy is kind of playing a role of pressure. It's just a constant that's appearing along that diagonal of the stress tensor. And then I have this term that, as we discussed, looks almost exactly the same. Oops, except for it has instantaneous quantities and it has my regular viscosity, not this eddy viscosity. So you can see why we call this, another reason why we call this the Reynolds stress tensor. It looks almost exactly like my stress tensor here, at least in this model. Certainly in units, it has the same units. So because it has the same units, we model it similarly to the stress tensor. It looks the same. But again, I have this new thing, which I don't actually know, so I need a model for that. And K is also, potentially difficult to compute. So I could include that in my model. Okay, so with that background, we can now discuss some of the most commonly used turbulence models. The first is what's called the K epsilon turbulence model. The K epsilon turbulence model takes those RANS equations, right? So we've got the equation, we've got the mass momentum equation, sorry, they're this one. But because I have these extra terms that I don't know anything to do with, I need to add more equations. So I'm going to add 2 more PDEs. One is this one, right? I have now an equation in terms of K, which I need, right? In terms for this model, I need the K. But I also need something for nu, and so that's going to be my epsilon. So I had another PDE that's for epsilon, and I didn't actually say what epsilon is. That's this dissipation term. Epsilon is dissipation. And so I'm not going to write what that is. There's a lot of details in this, but that eddy viscosity then is given by K squared over epsilon times some constant, I'll just call it gamma. So all of these turbulence models have these tunable constants, and the K epsilon one I think has 5 constants. So again, sort of kick the can down the road. I built a model, but now I don't know what gamma is, and there's 4 other constants I don't know. So these get kind of tuned based on experimental data. So if you choose the K epsilon model, there's going to be some defaults. But, in some cases, you may have to tune those constants. Most commonly, you might just use the defaults, but certainly in some cases, these are things that can be adjusted. This is perhaps the most commonly used model. So we have all the regular PDEs. We got the mass, momentum, and if we're doing the compressible, then we got the energy. So we have those potentially 5 PDEs already. We had 2 more PDEs, one for K, kinetic energy, and one for epsilon. And we solve them all together. We've got those adjustable constants. Again, like I said, K epsilon is the most commonly used one, but it, isn't good for everything. So I'll at the end maybe talk about some rules of thumb in choosing, but a variation here is what's called the K omega. And omega is just, it's a ratio of these things. So it's kind of similar, K omega model. Similar idea, has 2 PDEs, one for K, kinetic energy, now one for omega. This model tends to work better for compressible flows. This one has some limitations in compressible flows. This one tends to be a little better. It also tends to be better in the near wall, like as we get closer to a wall. So this one happens to be better, in the general flow field of resolving the turbulence. This one happens to work better near the wall. There is a model called the Mentor SST model that blends these two. I don't think this is an option in star CCM. That's something we're using in class. These are both options for sure. I don't believe this is an option, but the Mentor SST is a popular model that basically is a combination of these two. We'll use the K omega in the near field, or near a boundary layer, sorry, and then K epsilon further away, which is kind of where they're best at. So it's kind of the best of both worlds, if you will. Okay, so those are very commonly used ones. Another popular one that's simpler is called the Spilart-Almaris turbulence model. This is a one equation model, whereas these both have two PDs. This one has one. It's simpler to use. It's really designed for aerospace type applications, where most aerospace applications, like on an airplane, for example, at least under normal conditions, we don't expect to have much separated flow, right? We're going to have a boundary layer and then a very small sort of shear layer. And that's where the Spilart-Almaris model works really well. If you have separation, then this is not a good model to use. It's not, and in fact, it's not a good model for general use. It's really, like I said, sort of these high Reynolds number aerospace type applications where it's been tuned to. So we use it a lot for airplane type things. But if you're doing like a wind turbine, for example, it's not a good model because of the mixing and the separation and the large scale turbulent structures. The K epsilon is a more appropriate model in that case, as it's incompressible, but a lot of mixing and turbulence in the free stream. That one is also definitely a choice in star CCM. The last one that I'll mention is called the Reynolds stress turbulence model. This one is different. It does not use this Boussinesq hypothesis. So rather than trying to estimate this value for nu and k, it just tries to model the components of this stress tensor directly. So there are 6 unique components there, and so it has a separate model for each term there. This is the most computationally intensive, perhaps less commonly used, but is an option, right? And it could be a more accurate one if some of these others are not effective. Right, so I think I gave some of the recommendations. These are mostly incompressible with separated. This Spilart-Almaris aerospace, non-separated. When you have separation, a lot of mixing, this is good for incompressible, this is good for compressible. This is better in the free sort of the flow field, this is better near the wall. Mentor SST kind of combines those two in a good way. All right. Let's see, maybe I'll talk about this briefly. Last sort of concept. I'm not going to derive this, but there's the vorticity equations where I take the Navier-Stokes equations and I take the curl of the vorticity equation. And I'm not going to write the whole one, but let me just write the shorter version where I eliminate some of the terms if I assume that it's a constant density, like so incompressible. Then omega, remember omega is my vorticity. So I took the curl of the whole Navier-Stokes equation. And so, I'm going to get, instead of velocity terms, I'll have vorticity terms. And this is a useful equation for many reasons, but one I'll show here to motivate some maybe some limitations of some turbulence models. So I get these two terms here. And again, I'm not going to go in detail, as you can see more in the book, but this term here, this is my viscosity. This is the vorticity diffusion. This looks just like thermal diffusion. If you compare it to the heat equation, this is the heat diffusivity. So it's the same idea. It's kind of how the vorticity diffuses or spreads out due to viscosity. This term here is a stretching term. So it kind of stretches and tilts the vorticity vector. And this stretching, although it may be not obvious unless you write this out, this only occurs in 3 dimensions. So if I have a 2-dimensional flow, this term is always 0. But in 3D, this is what causes vortex stretching. And that stretching is essential for this kind of energy transport, this transfer of energy on the different scales. And so this is actually kind of a philosophical thing in turbulence, is that fundamentally it's 3-dimensional. Like, it doesn't really make sense in 2D, because in 3 dimensions, you get that stretching into the other dimension, right? Across the vorticity, you get the vortex stretching the dimension. That's what causes that energy transfer. And so you don't really have turbulence without 3 dimensions. And yet we use RANS in 2 dimensions all the time. So it's a bit of a debate whether doing 2D RANS is really useful. If it's maybe perhaps more accurate to use these lower fidelity methods, things we've talked about early in the semester, like a potential flow solution combined with the integral boundary layer method. Maybe that's a better approach, more accurate, even though it's, more fidelity. In practice, though, RANS 2D tends to work quite well. So maybe it's just more of a philosophical debate, but it is something to be aware of as an aerodynamicist, that you'll, hear this about 2D turbulence and whether that makes sense. The last thing I'm going to say briefly is something in between the two, right? So we talked about DNS, simulate all the scales. We said that's just impossible, right? Except for really low Reynolds numbers. RANS, let's forget about really all the unsteady behavior, just average it all. Let's look at what's kind of happening on the aggregate. Well, something in between the two is called Large-eddy simulation. And this is kind of a nice approach to the basic idea is that we can't go all the way to DNS, right? Because the problem is we get to smaller and smaller and smaller scales. So with LES, what we're going to do is we're going to resolve the big scales. We're going to try to solve the turbulence, use the Navier-Stokes equations directly to solve kind of the big scales. But as we get to really small scales, we're not going to solve them. We're not going to take our mesh finer and finer. We're going to use a model. As we'll see next time, there's reason to hope that this should work quite well, because many of at the small scales, there's a lot more things that are universal. We can get more universal scales, more universal scaling. So we expect that we can develop models that should work quite well at the small scale and not have to resolve them all. And again, there's a lot of theory that goes into this. I'm not going to get into it. Just want to make you aware of that. This is in between. Certainly much more computationally expensive than RANS, maybe an order of magnitude more computationally expensive or two. But it opens up the possibility to do these unsteady simulations at high Reynolds numbers. So again, particularly important for cases where I need that, things like acoustics, structural dynamics, or I need to see the time history, well, I should say we can do time varying RANS, right? It's called unsteady RANS, but we've still averaged out the behavior. In other words, things can change in time. So I can have an airplane that's doing an unsteady maneuver, but at each instant in time, I've averaged out the flow behavior. I'm not looking at, so if I go back to this picture here, it would be like I've got this flow thing here. Each instant in time it's averaged, and I could move it around, right? That thing could change, but I'm still averaging the flow field at each instant in time. So just to make that clear, I can have unsteady RANs, also called URANs. That's fine. But sometimes I need that structure. I need to see the actual fluctuations in my quantities for many reasons, and to really understand the flow behavior. This is used a lot in, for example, wind farm simulations where I need to see that wake mixing. If I average it out, then I may not capture the right behavior when I'm interacting with other wakes and with the atmosphere and so on. So anyway, just want to make you aware of that. Next time, we'll talk about turbulent boundary layers. It'll be a little quicker. I'm not going to go into too much detail, but we'll see some of that universality at small scales, and also some things that will come up in CFD.